I think we're live.
Oh, look, we are. Hello, everybody. This is Absolute Zero. I am Rachel Appel.
And I am Bertrand Leroy. And yeah, last week we talked about why the sky is black at night. And this week we're talking about why it's blue during the day.
Okay.
And it's an interesting one, actually. It's there are many different things to say about this. So this started. This is kind of a question that everybody has had at one point in their life, except that physicists actually keep asking the question, right?
Okay. And they have math behind their answer.
Yeah, well, not just math, also experiments. And actually, the first guy who had a beginning of an answer about this question was John Tyndall.
Okay. John Tyndall.
And that happened during the 19th century, in 1859. So that guy thought that he had the answer. So he was actually studying infrared radiation, and to study that, he needed to use containers of completely pure air. So he needed air without any dust whatsoever. And here's the thing that he did. He used to shine intense light onto a container of air. And if you do that, you will see the little particles of dust, right?
Yep.
Like you do on a bright day when the light shines through the window, right?
Yep.
And so he would purify the air and try again until he had something that was good for his experiment. And as it often happens, he noticed something about this, which is that the light that was scattered by the little particles was blue. It was more blue than the light that he was shining onto the container.
Okay.
And you can actually make the experiment. You take a transparent glass and you put a little bit of milk inside of that you mix into water, and then you shine a bright light on it. And you look at the light that goes through and the light that gets scattered by the particles of milk in the water. And you will see the light scattered is blue-ish, and the light that goes through is a little redder than the light that went in.
Oh, how interesting. Okay.
That's like the sky.
It is. It's a little bit like the sky, and part of it a sunset in the sky.
Not just a sunset, even during the day, the sun appears yellow. Whereas if you look at people didn't know that in the 19th century, but actually if you look at the sun from space, it's white.
Okay. I didn't know that.
So that looked like a great answer, but that's not the end of the story, because of course, why does the scattering of light produce blue light, right? But he did hypothesize that particles of dust in the atmosphere were responsible for the blue color of the sky, but actually he was wrong.
Because it's the air instead, right?
Well, yeah, it's a lot of things actually. It's the molecules in the air, but it's not really dust. So dust does participate in the phenomenon, but not enough. That's not nearly enough. And it's not until Lord Rayleigh studied the phenomenon that we really understood what was going on. And even he had only part of the answer. So Lord Rayleigh was that's not his real name. His real name is John William Strutt, and he was the third Baron Rayleigh.
Okay.
Yeah. So he was an aristocrat in Britain at the end of the 19th century, beginning of the 20th, and he actually got the Nobel Prize for something completely different. What was it? He got the Nobel Prize for... Can't find it. Yeah, he studied a lot of things. Can't find it. Interesting. But anyway, he's the guy who understood what was going on here. So
Okay.
here it is. So he built on the work of Maxwell, of course, which was the hero of that time before we understood relativity. Maxwell is the guy who understood that light is vibrations of the electromagnetic field, and he wrote the equations for the evolution of the electromagnetic field. So the thing about electromagnetism is that you have this field that's composed of an electric part and a magnetic part that interacts with charges, electric charges. Okay.
Right.
And if you apply an electric field, for example, on charges, it moves those charges, right? We all know that. It's the same thing that happens with static electricity. You have an electric field and charged particles get attracted by that, right? So if you put a charge in an electric field, it's going to move. And depending on its charge, it will move in one direction or the other direction. Now take a molecule. What's a molecule? Or an atom, even an atom. Just take an atom. It's a positively charged nucleus surrounded by a cloud of electrons.
Right.
Nucleus is positively charged, electrons are negatively charged. Apply an electric field, what happens? The electrons go one way, the nucleus goes another way. So now you have what's called a dipole, right? So you have a different distribution of charges, even if it was neutral before, now you have plus here, minus here. Okay, under the influence of the field. If you remove the field, it starts vibrating.
Okay.
Okay. So if you have an electromagnetic field such as light is just a wave of an electromagnetic field. So if you have molecules or atoms, they will start vibrating in that field. And what vibrates, when you have charges vibrating, this also emits an electromagnetic field.
Okay.
Just by applying the equations of Maxwell, the Maxwell equations. So there you have it. You have light coming in onto atoms and molecules.
Well, that field looks blue to us, right?
I'm coming to that. Okay. Exciting those charges. So because that takes energy to do that, right? So you have light coming in. Part of that light is going to excite those molecules and those atoms. That is going to absorb some of the energy. And then those atoms and molecules are going to reject that energy, but in different directions. That's why it's called scattering. Because it comes in from a specific direction and it comes out in all directions. So that's scattering. And the reason why it's blue is a little more complicated. When you do the calculations of what wavelengths are more efficiently processed by this, you see a spectrum that has a lot more light in the bluish violet parts of the spectrum and less in the reds.
Okay.
Which means that it looks blue.
Okay.
And the part of the sunlight that was absorbed and scattered by this phenomenon is the blue part, which means that you are removing blue light from the sunlight. So what goes through appears to have less blue, so it appears more yellow.
Okay.
And then you have, well, there is a lot of additional subtlety. We don't need to go into that. This is the big picture. You can wonder, for example, why it's not more violet than blue, and there are good reasons for that as well, but we don't need to go into those details. The general story is here. So that's what Rayleigh discovered and understood. And then we had some refinements around that. We understood, thanks to an Indian physicist called Rayman, that there is also the rotation of molecules that has an importance in there. And his actual real important discovery was that the shape of the molecules would influence the way they vibrate. Because the electrons are spread around more atoms in a complex molecule. And the way those molecules vibrate, that influences the spectrum, and it's called a Raman spectrum. You can, just by looking at the light that is scattered by the sky, you can recognize the molecules that are in the sky.
Okay.
That are in the atmosphere. So you can recognize, okay, well, that looks like the spectrum for this organic molecule, for example, and discover that it's there. So you can analyze the composition of the atmosphere just by looking at the light that it scatters.
That's kind of cool.
It is. It's very cool.
That's a handy little trick.
Yeah, it's very, very cool. Yeah, so that light is bluish. And you also know why the sun appears more yellow. And during a sunset, it's the same phenomenon, but it's more of it because the amount of atmosphere that the sunlight has to go through is larger. So there is more scattering that's going on. So you move the spectrum farther into the reds.
Right, right.
That's it. And then there is polarization, because that whole thing also explains why sunlight, well, not sunlight actually. Sunlight is not polarized. What is polarized is the scattered light from the sky. If you look at the sky using polarized glasses,
okay,
provided there are two kinds of polarized glasses, but you can remove the glasses, turn them like that, and see if you see a difference. And look at different parts of the sky and see if you see a difference. And what you will notice is that when the sun is high up into the sky, you will notice the most difference around the horizon. And when the sun is setting or rising, then you will see the most difference on a line that is above you. So that means that the polarization is mostly happening on a plane that is perpendicular to the direction where the sun is, right? Yep. So if the sun is here, you will have your polarization all around here. Can you guess why?
Well, just that angle that the light is coming in.
So, yeah, it has to do with that. But in order to understand that, what you need to understand is...
Well, is it also like, I don't know, is the light bending or something as well? Or?
Well, it is. There is some refraction that's going on in the atmosphere, and it does have effects, yes, but that's not what is causing polarization. So in order to understand that, you need to know how what the light waves look like. So there are different kinds of waves. Sound waves, for example, are vibrating in the direction where they propagate. You know, if a sound wave is going in this direction, the vibration that is propagating is actually going in the same direction. Light is a different kind of wave. It's what's called a transverse wave, where the oscillations of the field are happening in a plane that is perpendicular to the direction of the light. So if the light is going in this direction, you might have the electric field vibrating in this direction and the magnetic field in this direction, for example.
Right.
So that would be light polarized in one specific direction. Or it can rotate or so on. But the variations of the field are perpendicular. There is no component of the field that goes in the same direction as the wave. So let's say that the sun is here, it sends a wave here. So you have this plane here, which is where the molecules oscillate, okay? Well, the field oscillates. I'm going a little too fast. And the field is what makes the atoms vibrate, like we've explained before. So what direction are the molecules going to vibrate in? Same direction as the field, right?
Right.
So the vibrations of the atoms is contained in that plane. Okay? The molecules are not going to oscillate in this direction. They're only going to oscillate this direction or this direction. Okay? But you're not looking this way. You're not looking at the same direction as the sun. Let's say you're looking from the side here. What do you see? You see only vibrations in this direction.
Right.
And there you go. It's polarized in this direction. And if I put my polarized glasses in the other direction, I'm not going to see anything.
Then it's a different, from the different angle that you're looking at it.
Yes, exactly. So the sun is here. Okay, I'm only going to see polarization when I'm in the right, when I'm looking in the right direction on the sky. So that means on the horizon when the sun is at the zenith, and on the horizon when on a big circular meridian up in the sky when the sun is setting or whatever. And this is something you can easily verify with polarized lenses or filters or whatever. It's a very neat experiment, actually.
That is an interesting experiment to do.
So there you go.
So really just about the angle of the light that comes in versus the angle that you're looking at it.
Yep. So now we know why the sky is blue, why the sun is yellow, and why the light from the sky is polarized.
Basically, it's all an optical illusion.
And you know what? All that is one single thing, and that's the magic of science. It's explaining a whole range of phenomena with one single explanation.
That's kind of cool. I like that, short and to the point.
Yeah, it's super cool. It's unifying things. It's making things simpler. You have less concepts to explain a whole range of things. That's what's magic about science. That's why I love science.
That's funny that you say that. But it is. It's like magic about science.
Yeah, I love it. All right.
Cool. Now we know.
Yep, that's pretty cool.
Yes.
That's what I had.
We have a cool experiment to take out of that too. So.
Yeah, several actually. You can do the one with the glass of milk. Diluted enough that you can shine a light through it. And there is the experiment about the polarization. Cool stuff.
Yep. It's cool when you can do your own science.
Yeah, you can. Okay. Right. That's what we had for this week. Oh, no, I had another thing that I wanted to talk about.
Okay.
A few weeks ago, as you remember, we talked about Bayesian probabilities and what does it mean to be a Bayesian, I have a problem with that word, thinker. And I said a couple of stupid things. I was wrong.
Oh.
Yep. Okay. And I discovered that I was wrong by reading Sean Carroll's latest book, which is called The Big Picture. And I really recommend that book. It's so good. Sean Carroll is one of my two favorite physicists right now. I really love that guy. He's a remarkable guy. He's a good physicist, and he explains things very well. So in his book, he does explain what it means to use Bayes' theorem efficiently. Okay. So what I did say that was a little stupid is that in order to use, so let's say again what this theorem is saying. This theorem is helping you compute the probability of something given a prior probability and the probability given a specific outcome of another hypothesis. So let's say, for example, that you have an idea of how likely something is, like you throw a die and you think that there is 1 out of 6 chances, but then you learn something new, such as yeah, well, we know that for some reason the result is going to be odd. So knowing what you know now, you can reevaluate the probabilities. Probably not the best of examples, but anyway. And that theorem enables you to calculate those values. But the problem is you need a prior estimation of the probability. And I was criticizing people overusing that theorem because they sometimes don't have a good idea of what their prior is. But it happens that was a misunderstanding on my part because it actually doesn't matter. The whole point is that actually the priors don't matter. So you can start with an idea or its opposite. The point is that if you apply the Bayes theorem long enough and with enough additional data, you are going to converge.
Right.
You're going to converge to the right answer sooner or later.
Okay. That makes sense.
So let's say, for example, yeah, I think the probability that God exists is 80%. Okay, that's fine. You can actually take that prior as long as you take new evidence in, new data, and you reevaluate that probability and converge to something. You might actually arrive to the same probability as somebody else.
Right. Okay.
So I was wrong. Now the problem is that for this to work, you need to actually apply it and have a good estimation of those new probabilities, the probability given that new information that you get in. And you need to actually apply the formula and have a quantitative evaluation of that new probability. And that's where obviously most people actually fail and don't bother to do it. And they just, continue to...
Probabilities are hard.
Yeah. To estimate probabilities in ways that are completely anti-scientific. But the prior thing I was entirely wrong about. So I learned something new, and yeah, that's cool.
Nice. All right. I put that book in the list.
Oh yeah, you should. It's awesome. So sorry, I talked a lot today.
That's okay.
Okay, that's what I had.
Yeah, I'm coming off of a cold anyway, so.
Oh, okay.
My throat's a little scratchy.
Your brain is a little.
Yeah. Well, I say that's like kind of all the time. But.
Okay, and next week you're going to be around, you're going to be here, and you are going to be able to spread all those germs to lots of people.
Well, I'm over the contagious part, so.
Oh, okay.
Good. Just the normal cooties.
Maybe you'd catch something else.
I don't even, because I gotta go to Sweden after.
Always traveling.
Tomorrow starts a month-and-a-half-long travel spree. It's
ooh, nice. Yeah. Good for you. Nice.
We'll see at the end of the month and a half.
Yeah, you're gonna be. I want to go home. Okay, let's not bore people with all those details.
Right.
Bye, everyone. We hope you like the show.
Till next week or whatever.
Maybe next week. We'll see.
Right.
Cool. Bye-bye.